Hello all. In the previous presentation, we had a very brief introduction of the different logical systems like propositional logic, predicate logic, and modal and temporal logic. Now, from this presentation, we will be discussing the second half of the first module. The second half of the first module deals with propositional logic. So, starting with this video lecture and the coming few lectures, we will be diving into the details of propositional logic. So, welcome you all to this presentation on propositional logic. The contents of this presentation will be like, we will discuss what a propositional logic is, the syntax of propositional logic, a formula in propositional logic, and how to represent a formula in propositional logic as a tree as well as a string. So, coming to propositional logic. Propositional logic, it is the simplest of all the other logical systems, as well as it is the basis for all other logical systems. So, every other logical system is actually an extension of the propositional logic. And here, formulas are built from atomic propositions. Atomic propositions are those statements which cannot be decomposed further. Atomic propositions, they can be assigned the truth value true or false. 6 is a prime number, is an example for an atomic proposition. And see, the statement 6 is a prime number has got a truth value false. So, this is an atomic proposition which is having the truth value false. Now, again, 1 plus 1 equals 2. That is an atomic proposition whose truth value is true. And these atomic propositions can be combined using logical connectives or Boolean operators to form formulas. And some of the logical connectives are and, or, implies, etc. So, suppose we have an atomic proposition, say 1 plus 1 equals 2, and another atomic proposition, 6 is a prime number. We can combine these two using AND operator. Now, when we combine these together to form a propositional formula, see, this propositional formula will be also having a truth value. And that truth value will depend on the truth value of the operands and the meaning of the operator. So, in this case, we have true and false. True and false will give a result as false. So, when we consider a logical system, logical systems usually formalizes reasoning. And a logical system is similar to a programming language. You might have learned several programming languages. See, when you consider the programming language C or Python, you know that the language will have a defined syntax and semantics. If it is the C language, it will tell you how to write an assignment statement, how to write a loop, how to write a control statement like if, and so on. Right. So, it will have a defined syntax and as well as it will have a semantics. The same way, logical systems also will have a defined syntax and semantics. The syntax will define what strings of symbols will constitute a legal formula in that particular logical system. And the semantics will define what these legal formulas mean. Okay, so we have a defined syntax and we should confine to the syntax to write legal formulas in that particular logical system. Now, considering the syntax of propositional logic. In propositional logic, to construct formulas, we know that we need atomic propositions and we need Boolean operators. This atomic propositions, it's an unbounded set of symbols which is denoted using the notation P. And this set P consists of the lowercase letters in the set, say set P, Q, R, etc. Okay. So, to represent an atom or to represent an atomic proposition, in propositional logic, we use the notation say P or we use the notation Q or R, etc. Okay, an atomic proposition is also called an atom because we cannot actually decompose an atomic proposition further. So it is called an atom. Okay, so we can represent an atom using the symbol say P, another atom using the symbol Q. Suppose we have an atomic proposition say 1 plus 1 equals 2, that we can represent using an atom say P. So P may denote say 1 plus 1 equals 2, and Q may denote say sun rises in the west. And we can join these atomic propositions or atoms using Boolean operators. And the Boolean operators that can be used in order to combine the atoms is also defined in propositional logic. And see, this is the set of Boolean operators that can be used. We have negation operator, disjunction operator, which is actually our OR operator, conjunction, which is again our AND operator, implication, which is implies, then we have equivalence, exclusive OR, NOR, and NAND. See, when we consider disjunction, we know that when we have a formula, say P or Q, the truth value of P or Q will be false only if both the operands are false. That is, P as well as Q should be false for P or Q to be false. Now coming to conjunction. Conjunction, we have say suppose we have the formula is P and Q. P and Q will be true only if both P and Q are true. In all other cases, P and Q will be false. Now, when we consider implication, P implies Q will be false only if P is true and Q is false. And when we consider the equivalence operator will give the result true if both the operands are the same. That is, if both P and Q is having the truth value true, then P equivalence Q will be true. Or if both P and Q is having the value false, P equivalence Q will be false. Now coming to exclusive OR. Exclusive OR will give the result true if both the operands are having different truth values. That is, if P is true and Q is false, P XOR Q will be true. Now coming to NOR and NAND. These two are actually negations of OR and respectively. So NOR is actually the negation of the disjunction operator and NAND is the negation of the conjunction operator. So that is regarding the operators in propositional logic. So using atoms and the Boolean operators, we can construct formulas in propositional logic. Now coming to a formula in propositional logic. See, a formula in propositional logic can be represented either using a tree or you can represent it as a string. So first we will be discussing how to represent a propositional formula as a tree, and then we will see how we can represent it as a string. So coming to tree representation. See, a formula in propositional logic, it is a tree which is defined recursively. So see, a formula will be a leaf which is labeled by an atomic proposition. See, always in the tree, the leaves will be labeled with atomic propositions. The internal nodes as well as the roots will be labeled with operators. And we have two types of operator. Negation is a unary operator and all others are binary operators. So if we have a node which is labeled by negation, then that node will have only a single child, which is a formula. And if the node is labeled with a binary operator, that node will have two children, both of which are formulas. We will see an example. Suppose we have a propositional logic formula. Say P implies Q, equivalence, negation P implies negation Q. See here, this formula checks the equivalence of P implies Q and the negation P implies negation Q. So we can say that equivalence here is the principal operator. So we will use this principal operator to label the root. The root will be labeled with principal operator. So see here, principal operator is used to label the root of the tree. So root of the tree is the principal operator, which is equivalence. And since this is a binary operator, this node will have two children. Now coming to the left child of this particular node. See, as the left child, we have a formula P implies Q. Right. So when we consider this formula P implies Q, we extract the operator and we label this node with the operator. Okay. So this the child of this particular node, the left child of this particular node will be the implies operator. And implies operator again is a binary operator which will have two children. And the two children will be the atoms P and Q. And these actually will form the leaf of the tree. See here, implies operator has got two children and the two children will be labeled with its operands, and that operands are actually atoms. So using atoms we label the leaf of the tree. Okay. The same way we build the right subtree also. In the right subtree, the formula is negation P implies negation Q. Here again the operator is implies. So we will label this node with implies, and that implies is a binary operator. So it will have two children, and one child will be the formula negation P and the other child will be the formula negation Q. Okay. So when we consider the formula negation P, here again we have an operator and an atom. Right. So we label the root with the operator negation, and since negation is a unary operator, it will have only one child which is labeled with the atom P. So see here, this is how it looks like. We have implies, and implies will have two children. Both the children will be labeled with the negation operator. Negation will have only one child, and here the child will be P and here the child will be Q. Okay. So this is the tree representation of this formula. Now when you consider the tree representation of this formula, you can see that all the leaves are labeled with atoms, and the interior nodes as well as the root will be labeled with the different operators in the formula. Okay. So this is how you represent a propositional formula as a tree. Now we will see how to represent this as a string. See, to represent the formula as a string, what we do is, on the tree we perform in-order traversal. When we perform in-order traversal on the tree, we will get a string, and that string will be the string associated with the formula. And see, this is the algorithm for performing in-order traversal of the tree. This algorithm is similar to the one that you have learned in your data structures. In data structures, you might have learned to perform in-order traversal on a tree. The same thing is written here. See here, we have the in-order function. The in-order function is a recursive function. Okay, so to since it is a recursive function, to exit from this function, the condition is the formula should be a leaf. When the formula is a leaf, we write the label and we return. If the formula is not a leaf, then what we do is we perform in-order traversal on the left and the right subtrees of F. Okay, so we perform in-order on F1, then we write the label of the root of F, and then we perform in-order on F2. Okay, and again, if the operator, that is, if the formula, it is a negation operator, then what we do is we will have only one child. So we will have only one subtree. So if the formula F is a negation operator, then we consider the left subtree as empty. That particular node will be having only right subtree. Okay, so we will see an example. See here, this is our in-order function, and again here, when the root of F is say negation, the left subtree is considered to be empty. So this particular statement will be skipped if the root is negation. Now when we perform in-order traversal on this particular tree, we start with the root. The root, it is not a leaf, right? So we skip this part. Okay, and then we perform in order on F1 and F2, which are the left and right subtrees of F. So this is the left subtree and this is the right subtree of F. So first we call in order on the left subtree, right? We call in order here. Okay, again when we call in order here, we have again an operator, and since it is an operator and it is not a leaf, we again call in order on its left subtree. And now finally we have an atom P. Okay, we have the leaf. When we get the leaf, what we do is we write the label. That is, we write P and we return, right? So after writing P, we return, and what we do? Write the label of the root of F. That is, we will write the label at the root, which is the implies operator. And then we call in order on F2. Then we call in order on F2. F2 again is an atom, it's a leaf. So we write the label and we return from this. We reach here, right? We write the label at the root of F and then call in order on the right subtree. Okay, and when we call in order on the right subtree, again we have an implies operator. We call in order on the left subtree of the implies operator, and we have a negation. And see, negation is a unary operator, and since its left subtree is empty, see this part is empty. So what we do? We write the label at the root, which is negation, and then we perform in order on the right subtree. Okay, so we get negation P implies negation Q. So this will be the formula. P implies Q, P implies Q, equivalence, negation P implies negation Q. Okay, so this is how we perform in order traversal on a tree to get the string representation of the formula. Okay, so this is a string representation of the formula. Now, see, when we use this particular algorithm, say suppose we have a tree of, suppose this is our tree, the second one, this is our tree. Okay, perform in order traversal on this tree. When we perform in order traversal, what happens? We get P implies, then we call in order on the right subtree. So here we call in order on the left subtree, which is Q. So we have P implies Q, equivalence. Here we have negation. Then this is actually the right subtree of negation, right? So we print negation and then we move on to the right subtree. So we have negation, then we have P implies negation Q, right? So what happens is, when we perform traversal on this tree, again we get this formula itself. If we are performing traversal on this tree using this particular algorithm, we will get the same string. Whereas what we actually should get is this, like P implies Q equivalence negation of P implies negation Q. This is what we had to obtain. But what we get is this using this particular formula. Okay, so we have ambiguity in the string representation. That is, we have two trees which yields the same result, or two trees which yields the same string as output. Okay, so we need to somehow resolve this ambiguity. To resolve the ambiguity, one method is to use parenthesis. So in the same algorithm, we insert the code for inserting a left parenthesis and a right parenthesis. Okay, that is the only modification. The rest of the code is the same. We insert a left parenthesis and a right parenthesis in order to resolve ambiguity in the string representation. Okay, so this is the second algorithm, which is a modified version of the first one, where we use parenthesis in order to resolve ambiguity. Another method for resolving ambiguity is using precedence. See, we can define precedence and associativity among the operators. Like, see, when we consider the operators in propositional logic, the one with highest precedence is negation. Negation has got the highest precedence. Then comes conjunction and the NAND operator. Then we have disjunction and NOR operator. And finally, we have implies operator, and then the least precedence will be for equivalence and XOR. So this is the order of precedence. The order of precedence, higher precedence for negation and the lower precedence for equivalence and XOR operator. Okay. Again, say we also have to define associativity. Operators will associate to the right. That is, suppose we have a formula, say A or B or C. Here the operator is the same. Both the operators are disjunctions. Right. So if the operators are the same, this disjunction associates to the right, which means that first we will perform B or C, and then that result will be OR with A. Okay, so this actually means A or B or C. B or C will be the first operation that is performed, and then only we will perform disjunction on A and the resultant of B or C. Okay. Now, apart from this, if we need to change the order, if we need to indicate a different order, we will have to use parenthesis. In this case, even though we have disjunction and even though disjunction associates to the right, since we have parenthesis, we will give precedence for A or B. And to this result, we will perform disjunction of this result of this to C to get the result. Okay. And see, when we consider the Boolean operators in propositional logic, disjunction operator, conjunction operator, equivalence operator and XOR operator are associative, whereas the implication operator, NAND operator and NOR operator are not associative. That is, if we are using these operators, we will have to use parenthesis in order to avoid conjunction. There is no implicit associativity when we are using implies, NOR or NAND operator. Okay, so these are not these operators are not associative, whereas conjunction, disjunction, implies and equivalence and exclusive OR are associative, and these operators associates to the right. Okay, so that is how to resolve ambiguity using precedence. And finally, the third method is using the pre-order traversal. When we perform pre-order traversal, we won't have any ambiguity in the string representation. So the third method for resolving ambiguity is to use the pre-order traversal, or we call it Polish notation. The prefix notation or the pre-order traversal will give us the Polish notation of the formula. Okay, so here you can see the algorithm. This algorithm again is similar to the pre-order traversal which you have learned. So pre-order, it is a recursive procedure, and in pre-order traversal what we do is we first write the label of the root, then we check whether f is a leaf. If f is leaf, we return. Otherwise, we call the pre-order on f1 and f2, where f1 is the left subtree and f2 is the right subtrees of f. Okay, so these are the three different methods for resolving the ambiguity in the string representation of the formula. Okay, so the references to this topic, like see your entire first module, we will be referring to the textbook by Ben Ary. The textbook is Mathematical Logic for Computer Science by Ben Ary. So all the contents in this presentation and in all the future presentations will be from this particular textbook. And so in this presentation, what we have discussed is, we have seen what propositional logic is. We have seen the syntax of propositional logic. We have seen how to represent a formula in propositional logic. We have seen how to represent a propositional logic formula as a tree and as a string. Also, we have seen the ambiguities that arises when we represent formulas as strings, and we have seen the different methods for resolving the ambiguities, like using parentheses, using precedence, then using Polish notation. Okay, so these were the topics that we had discussed. Thank you.